want to do the, actually the whole first page. So that must be foundational materials there. Let's look at number 1. Actually, I can use the whole board. My brain in gear. Here we go. Okay, a gas absorbs 0 joules of heat and then performs 30.7 joules of work. What's the change in internal energy? Right. Definition of internal energy, remember, is that, well, actually not the definition, but any change in internal energy requires a change in heat absorbed or released, or a change of work done on the system or by the system. So I find it helpful sometimes to just draw a picture. This is our system. And if 0 joules of heat are absorbed, that means that this term just goes out. There's no change in Q. So we only have to look at W. So if the gas performs 30.7 joules of work, which way is the work going? It's going out. Right? So W is negative. And it's negative to the tune of 30.7 joules. So that's the only factor that counts. That means this is equal to 30.7 joules. All right, so that's why the answer is D, negative 30.7 joules. There's another one. Brandy's popping in. Okay, power's out. I'm running on batteries, and apparently the Wi-Fi is running on batteries too, otherwise you wouldn't be able to get me. So I'm just going to do an in-person review, and as long as it records, fine. If it cuts out in the middle, then I still have previous semesters recorded and in Blackboard. Okay, that was 1. Let's look at number 2. What's the kinetic energy of a 1.56 kilogram object? So mass is 1.56 kilogram. Let's see. Moving at 94 kilometers per hour. So the velocity is 94.0 kilometers per hour. Right, if we're going to determine the kinetic energy, we need a formula. And that happens to be kinetic energy equals 1/2 mass times the square of the velocity. But these have to be in SI units. In order for this to be joules, this has to be in kilograms, and this has to be in meters per second. Okay? So we're good here, right? That's kilograms. But we need to convert this to meters per second. So remember, when you have to convert 2 units or more, 2 or more units here in a measurement, do one at a time. So I'm going to do kilometers first. Right? 10 to the 3rd kilometers is 1 kilometer. So the kilometers cancel. We got our meters taken care of. Now we need to get rid of the hours. So does anybody know the conversion of hours to seconds? No? Well, we can do it. We can chain them together. How about that? Right, 60 minutes in an hour, correct? And that gets rid of hours. And now we get rid of minutes, change the minutes to seconds. So 60 seconds in 1 minute. So that gets rid of minutes. Okay. I could have given you the answer, but this is more fun. 3,600 seconds in an hour. Okay, so now all we have to do is resolve that to, let's see, 94 times 1,000 divided by 60, and then divided by 60. And that's, I'm going to keep a couple of extra. 26.11, how about that? Meters per second. Right? There's the second, there's the meters. Now we can plug those values in here. So we got 1.56 kilograms, and velocity is 26.11 meters per second, and we have to square that. Okay, so 26.11 and squared times 1.56 and divided by 2. So I get 5, let's see, 3 significant figures. 5, 3, 2 joules. And, oh, this is in scientific notation, so let's see. It's in kilojoules, actually. So how do we make kilojoules out of that? Well, remember, as the unit gets bigger, the number has to get smaller. So if we change the unit to kilojoules, that's 1,000 times bigger. So the unit has to be 1,000 times smaller. So we go 1, 2, 3. So that would be 0.532 kilojoules, but it's in scientific notation. So we have to write this in scientific notation. Right? Move it over 1, 5.32, and we store that tenth in a power of 10. Okay, so that's why the answer is A. 5.32 times 10 to the minus 1 kilojoules. That's how much energy that object has moving at this speed. Okay? Good. Okay. That's that was 2. And let's look at 3. Which of the following statements correctly describes the sign of Q and W for the following exothermic process at 1 atmosphere pressure and 370 K? So what we've got is water gas, and it's going to water liquid. So it's helpful, again, to draw a picture. So this gas, let's put this gas in a cylinder with a movable piston. Now, why would I do that? Because the pressure is constant at 1 atmosphere, and the temperature is constant at 370 K. All right? That means that whatever happens to this gas, in this case, it's condensing into a liquid. Right? So we're going from a gas to a liquid inside this container. And when it happens, the gas disappears and all you got left is liquid. Or, well, you have a little bit of water vapor at that temperature. But what we're doing is, if this is under a constant pressure, then that piston is going to drop. Okay? So it's going to end up way down here somewhere, and with liquid water on the bottom. Okay, the reason I'm going to all this trouble is to answer these questions, we have to say the signs of Q and W. Right? Q, well, they tell us it's an exothermic process right here in the problem. But you can deduce that from this. If you go from a gas to a liquid, it has to give up heat. That's the only way it can go from a gas to a liquid. So the exothermic process means this is a negative value. Right? Because heat is leaving the system. That's the system. Okay? Now, how about work? How about work? Well, when a gas contracts, work is being done on the gas. Think of it that way. As the volume decreases, right, because work is equal to minus P delta V. Pressure is constant, but what's the volume? The volume change is final minus initial. So final is less than initial. Right? That's what this term is. So if the final volume is smaller than the initial volume, that value is negative. And a negative times negative is positive. Okay? So work is being done on the gas. All right, so let's look at our choices here. A says Q and W are negative. That can't be. Q is positive. Nope. C, Q is negative, and W is positive. So C does answer the question. D, no, Q and W positive. Q and W are both zero. No. C has to be the answer to give you a negative Q and a positive W. Okay? Some of these problems look like you can just stare at them for a few minutes and the answer just goes, boom. Don't work that way. You got to logically pick the problem apart. All right, let's see, 4. For a particular process, Q equals 20 kilojoules. Okay, Q equals plus 20 kilojoules. And W equals 15, positive 15 kilojoules. Which of the following statements is true? Well, let's see. We do it like that, and that means both of them are being added to the system because they're both positive. Heat flows from the system to the surroundings. No, it's the other way around. So it can't be A. The system does work on the surroundings. No, it's positive. If it does work on the surroundings, it has to be negative. C, delta E equals 35. Well, is it true? Delta E equals Q plus W, 20 plus 15. Yeah, that's true. C is true. All the above, no. None of the above, no. So C is the answer to number 4. It's too quiet here. When I stop talking, just dead silent. We usually got, well, we got that machine whirring. And I think the air conditioning or the AC, HVAC makes a noise. 5. I guess I just have to constantly talk. No dead air allowed. Which of the following statements is correct? All right. A, the internal energy of a system increases when more work is done by the system than heat was flowing out of the system. Okay, let's look at this. Here's our system. And then we've got the potential for work and Q. All right, they could go either direction. In A scenario, the internal energy of the system, it's saying that delta E is positive. It's increasing. When more work is done by the system, so if work is done by the system, it's negative, then heat was flowing out of the system. That makes them both negative, so it can't be positive. If they're both negative, that can't be positive. right? So A is false. Okay, how about B? The internal energy of the system decreases. Okay, now I'm going to make it negative. When work is done on the system, and heat is flowing into the system, right? That's just the opposite and it's still wrong. So B is false. The system does work on the surroundings when an ideal gas expands against a constant pressure. That's the definition. The system does work on the surroundings. And that's not entered into it for C. It does work on the surroundings when the gas expands against a constant pressure, right? Work equals negative P delta V. That's true. That's the definition. So if that one's true, D and E can't be right either. All statements are true or all statements are false. So it has to be C. All right, let's flip the page and see. Let's skip to 7. Okay. 1 mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters. Okay. So we got. So carrying on. Let's see. 1 mole. All right. And the volume, the initial volume is 1 liter, and the final volume is 8.93 liters. Okay. And the pressure, constant pressure, is 1 atmosphere. Okay. How much work in joules is performed on the surroundings? First of all, let's see if that's true. Right? It starts off here at 1 liter, and then it ends up at 8.93 liters. Is that true? It expands? Okay, yeah. So work is being done on the surroundings as the gas expands. All right, so to answer the question, how much work in joules is performed? Right? What's the formula? Minus P delta V. So we get minus, pressure is 1 atmosphere. And delta V is final volume minus initial volume. Okay. So that gives us, let's see, that's 7.93. So it's minus 7.93 liter atmospheres. That doesn't look like joules to me. So I think we have to do a unit conversion. So let's convert this to joules. Minus 7.93 liter atmospheres. So we need a conversion factor that'll take liter atmospheres and leave us with joules. So what's the conversion factor? Oh, it gives it to us right there. 1 liter atmosphere is 101.3 joules, right? So we just multiply that times 7.93. Times. So I get 803. 803 joules. See, is that one of the answers? Oh, forgot the sign, didn't I? That negative right there. Negative 803. That's B. Okay. Let's see, number 9. That. Number 9. A fuel-air mixture is placed in a cylinder fitted with a piston. Okay. Piston. And we got our fuel-air mixture in here. Doesn't say what it is. I suspect they're going to ignite it and see what happens. The original volume is 0.310 liters. 0.310 liters. When the mixture is ignited, gases are produced and 935 joules of energy is released. So we've got an exothermic process with 935 joules of energy being released. So that's a negative. To what volume will the gas expand against a constant pressure of 635 millimeters of mercury? So we've got a constant pressure of 635 millimeters of mercury. All right. If all the energy is released and is converted to work to push the piston, okay, there's the key. It's all converted to work. Okay. So it's asking us for the final volume. Right? So if this is minus 935 joules is equal to minus pressure, 635 millimeters of mercury divided by 760, right? That'll give us atmospheres. Oops, this is joules though. We need to convert that to liter atmospheres. Probably. So minus 935 joules. You cancel joules and leave us with liter atmospheres. Right, what was that? 101.3, wasn't it? Yeah. So 101.3 times 935 will give us liter atmospheres. I can't put that there. And times 935. Let me check myself. So negative 9.47 times 10 to the 4th. And this is the liter atmosphere. This is the pressure. And the change is going to be final volume minus initial volume, 0.310 liters. So now we have an equation in one unknown. We just had to be sure that the units were right. That's what this step was about. And this is that. Okay, so I'm going to take this one, resolve that quotient, and then divide it into this one. Right? Because it's times on this side, it's in the numerator here, it's in the denominator over there. So let's see, 635, 60 divided, that gives me 0.8355. 0.8355, just in case I atmospheres. Just in case I mess up. Okay. Oh, there's Elijah. Okay. The reason we're doing it this way, Elijah, is because the power quit on us. So I started doing it on the board without the benefit of the screen. And we're just going to keep doing that in case the power cuts out again. Okay, so that one. Oh, you're clairvoyant, right? Did you hear that click, the door click? That was a power blip. Okay, so we're gonna divide this one into that value right there. Let me see if I've got them in order in my calculator. Yep. Okay, so now I've got 1.1336 times 10 to the fifth equals VF minus 0.310 meters. So I just add this one to that side, and that'll be our volume. And it didn't make much of a difference. 1.134 times 10 to the fifth liters. Now let's see. I made a math error, which I'm prone to do sometimes. Yeah, something went wrong. What did I do wrong? Probably right here. It's this many joules converted to liter atmospheres minus 935. Energy is released. It's negative, that's right. Isn't that the correct conversion? That many? No. That's my problem. There it is. That was the problem. So it's 935 divided by 101. So that's 9.23. There you go. So now I'm going to divide that by this one. And this is a negative. So I'm dividing by a negative. And that's 11.05. .05, and then add that to it. $11.4. Which one? Number 9. There it is. C. How easy it is to make mistakes. Okay, that was number 9. How about number 10? Yep, number 10. Which statement is true of a process in which 1 mole of gas is expanded from state A to state B? 1 mole of gas is expanded from state A, 1 mole, to state B. So it has to expand. The volume has to increase. Right. This is state A, and this is state B. When the gas expands from state A to state B, the surroundings are doing work on the system. Is that correct? That would make work positive. But an expanding gas is doing work on its surroundings, so that has to be negative. So this one is false. How about B? The amount of work done in the process must be the same regardless of the path. So they're saying W is a state function. Is that true? Sorry. Q and W are both path functions. So B is false. C, it is not possible to have more than one path for a change of state. Oh yeah, it is. Right? Different amount of work, different amount of heat transfer. You can have infinite number of paths to get from one state to another. Right, so this one's false. How about D? The final volume of the gas will depend on the path taken. Now that's not true. It goes from this volume to that volume. It may take different paths to get there, but once it's there, the volume is the same. Okay, change of volume in this case is a state. So D is false. How about E? The amount of heat released in the process will depend on the path taken. That is true because Q is a path function. The amount of heat exchanged, it says the amount of heat released. Now it doesn't put that condition on it. So the answer E actually puts the condition on it at the amount of heat released. Depends on the path. And that statement in of itself is true. I mean, we don't know if it's from the original statement, we don't know if it's doing that or not. But the statement all by itself is true. Does depend on the path. The amount of heat released does depend on the path. All right. Yeah, let's go down to 13. No, 13. Your document should have 13 crossed out, does it? Yeah, okay. I thought so. I got rid of that one. I think it was just a bad question all around, so I didn't want to deal with it. I didn't feel like correcting it. Let's see, there's plenty more to go around. How about 14 through 17? These are all based on that statement at the top of the page. So the statement at the top of the page says, a gas in a 1 liter bulb, so that's 1 liter, is connected through a valve to another bulb that's initially evacuated. So we've got a valve connected to another bulb, and we don't know how big this bulb is. But that's a vacuum. Okay. What is true about the value of Q? Oh, wait a minute. There's more to it. Answer the following questions. When the valve is opened. Okay, when the valve is opened, at STP, standard temperature and pressure. So the temperature is going to stay the same. And as the gas expands, the temperature is not changing, right? Because it's all at standard temperature. There's no heat transfer at all. So Q is 0. Okay. That's equal to 0. That's B. How about 15? Work being done. Is work being done? No, because it's not working against any pressure. It's just moving from here to there. Right? There's not a piston moving against a pressure. It's just moving to fill that space. So there's no work being done either. That's probably B also. How about 16? True about delta E. Well, delta E is Q plus W. If both of them are 0, then Q has to be equal to 0. How about 17? True about delta H. Well, delta H is equal to Q if what? Constant pressure. Now that one might take a little thinking for a second. My initial impulse is to say that that's also zero. Delta H is zero in this case. Simply because the pressure is constant, the temperature is constant. But if delta H is equal to Q only when the pressure is constant, if you look inside here, then the pressure is a certain amount here, but if you expand it into a larger volume, what happens to the pressure? According to Boyle, the pressure goes down. So that one might be questionable. I tend to want to say it's zero simply because it's a state function. And it's equal to Q if the pressure is constant. But that's kind of iffy. What would it be? What would delta H be if, what was that formula? Delta H equals delta E plus delta PV, right? I think that was it. So if delta E is zero, the volume increases, pressure goes down. So is there a change? Actually, there's no change in P and V at all. Right? There's no change in P and V because they balance each other. One goes up, the other one goes down. So that one's also zero. That's my logic for saying that this one is zero. Now, my guess is that probably just flew right over your head. So when in doubt, take my word for it. Under these conditions, delta H is zero. Let's do wet my whistle. Let's go to number 19 now. Number 19, which of the following properties is or are intensive properties? So we got these choices. 5 of them? Yeah. Okay, which of these intensive properties? Mass, temperature, volume, concentration, or energy. Okay. Remember that what is an intensive property? It's one which describes any change that, or any property of a substance that does not change with amount. How about mass? That's not intensive, that's extensive. The more substance you have, the more mass you have. How about temperature? That's intensive. Any place you measure a substance, once the homogeneous temperature is established in the substance, temperature will not change anywhere you look, no matter how much of the substance you have. Temperature is intensive. The more substance you have, volume increases. Concentration, that's intensive. Right? Once you know the concentration, it doesn't matter how much of the mixture that you have, it's still intensive. This value is constant no matter how much of the substance you have, as long as you've established the concentration value. So these two, 2 and 4, are intensive. Energy, now if you have more, and this is extensive. Energy can increase with the amount of substance. Okay, so the only two, 2 and 4 would make it C. Would be the answer for that. Let's see, I'm doing time. Okay. Let's see. 23 refers to this equation. Okay, that's ethanol, the drinking kind. We're going to burn it. And this equation is balanced. Under standard conditions. That's why the water here is liquid and the ethanol is liquid, because this is under standard states, and the delta H for this is minus 1.37 times 10 to the third kilojoules. Okay, consider the following propositions. Roman numeral 1, the reaction is endothermic. Is that true? No. That negative sign right there? That's exothermic. That energy is leaving the system. So 1 is false. 2, the reaction is exothermic. Okay, yeah, we just said that. How about 3? The enthalpy term would be different if the water formed was gaseous. This is definitional. Enthalpy depends not just on the compounds and elements in your reaction, it also depends on their state. Right? So if you change the state here, you change the enthalpy. So that means 2 and 3 are both true. And that means E is the answer. Okay. Let's see. Before I leave that equation, I have a sneaking suspicion it pops up again later. Let me just take a second to look. Yeah, there it is. But I don't call on that one. Let's see anywhere else. Oop. Maybe I just dreamed it. Maybe one of the other problems doesn't give you the formula, it just tells you in words. Nevertheless, we shall move on. All right, that was 23. Let me see. Okay, 24. Now we're going to get into a little calorimetry. How much heat is required to raise the temperature of 5.75 gram sample of iron from 25 to 79.8 degrees Celsius? Right, this is really simple. What's the definition? Q equals specific heat times the mass times the change in temperature. That is, if the specific heat is in terms of mass, joules per gram degree C. If it's in molar quantities, then you would have to change the mass to moles before you could use it. But in this case, we're good to go. So specific heat for iron is 0.450 joules per gram degree C. Mass is 5.75 grams. And what's the delta T? Final minus initial. 79.8 minus 25. Okay. And then we just do the calculation. And in the interest of time, I'm not going to do that. I'm just going to say 142 joules, which is E. Okay. That's how you set it up anyway. I'm gonna skip 25. Just because we don't have a lot of time. Go to 26. 26 is another calorimetry problem. 32.5 gram piece of aluminum with a molar heat capacity of given there is heated to 82.4 degrees and dropped into a calorimeter containing water with this specific heat capacity given at an initial temperature of 22.3 degrees. The final temperature of the water is 24.2 degrees Celsius. Calculate the mass of the water. Okay, so remember, this is an isolated system. The calorimeter is isolated, which means what happens in Vegas stays in Vegas. Everything has to add to zero inside that calorimeter. And then we've got several things going on. We've got the heat transferred out of the aluminum, and then we've got the heat transferred into the water. And it doesn't give us any information about the calorimeter itself. Right. So we have to ignore the correction for the calorimeter. Okay. So we only have these two factors. In this case, the specific heat is in terms of mole. It's molar heat capacity. So what we have to do in order to use it, we've got to convert the mass of 32.5 grams of aluminum to moles. So we need the molar mass of aluminum, which is 2698. So that'll tell us how many moles of aluminum we have. The reason I know that is because the heat capacity for aluminum is given in terms of moles. So that's 1.205 moles of aluminum. All right. So now we can set up our problem. All right. So let's do it over here. The Q for aluminum is going to be the specific heat capacity for aluminum times the mole, actually the molar heat capacity for aluminum, times the moles, times the change in temperature, and then add that, the specific heat capacity of water, times the mass, times the change in temperature. So the value for S for aluminum is given as 24.03 joules per mole degree C. The number of moles is 1.205. Okay, so now I can erase this. And then the change in temperature is final minus initial. So the final temperature is 24.2 degrees. That's where it finally settled after we dropped the aluminum in. Minus, what did it start as? 82.4 degrees. Okay, that's the aluminum. Now, this is the water. 4.184, is it? Well, they just use 1/8. Okay, so we better use that value. Joules per gram degree C times, that's our unknown, the mass of water. Okay. And its final temperature is the same, but it started at a different temperature, 22.3 degrees. There we go. So now we've got that problem set up, and this is all equal to 0. That plus that is equal to 0. So what you have to do is say, what's that difference in temperature? Times this, and that'll give you a negative number. Okay? Because this one is bigger than that one. This one will give you a positive number, times that one, times this. So if we solve all that, then the mass of water should be 212 grams. The rest of it is number crunching. Okay. That's how you set it up. Let's see. 29 is an interesting problem, but it's going to take too much time, and I got a couple other things that I need to get to first. Okay, 30, we can do 35 pretty quick. You know, the other thing I can do, I did this exact same thing yesterday at Greenbrier. So I could put the link for Greenbrier up as well in our Blackboard course. Okay. Because we had more time there, and I went through and I was able to actually work those problems out in real time. So I think I'll do that. So you have both this video and theirs. In fact, theirs will probably be ready earlier because I've already started processing it. Okay, if 5 kilojoules of energy is added to 15.5 grams of water, the water is what? Boiling, vaporized, frozen, decomposed, still liquid. So how do we know whether it's a liquid or boiling or vaporized? Temperature. What's the temperature of the water? Okay. So how do we do that? Well, Q equals S M delta T. And we're starting at 10 degrees. So initial temperature equals 10 degrees C. And this is equal to Q, and this is the mass. Okay? Q needs to be in joules. 5.0 times 10 to the third joules. Right? I just took this right here, that K, which means 1,000 times, and turned it into 10 to the third. So S for water is 4.184. And the mass is 15.5 grams. And the final temperature is our unknown. We want to know what temperature it is right now. Minus 10 degrees. There you go. So I am going to have to solve this one because otherwise I can't answer the question for you. All right, so this times this, 4.184, 15.5. This term right here is 64.85. So we've got 64.85 times TF minus a negative times this 64 would be 648.5. Okay, is equal to 5 times 10 to the third. So now bring this over here as a positive and add it to that one. Let's see, what is that? 5,000. And then this one becomes a positive on that side, 648.5. So when I bring this one over here, we get 5.649 times 10 to the third equals 64.85. Final temperature, and then I should divide both sides by this value. And final temperature is equal to 87 degrees Celsius. So what form is the water? It's still liquid, right? It's a hot liquid, but it's still liquid. That means the answer is E. Let's see. Okay, we'll do this. I generally don't like to solve problems that have generic fillers like A, B, C, and D. I'd rather do real compounds and real elements. But in this case, number 55, using these fill-ins, A, B, C, and D, it helps to remove the complexity from the problem so that you can actually see what's going on. So we've got these three to work with, these three equations. Yields 2C plus D, and the delta H for that is minus 125. We also have 1/2 A yields B, and that's 150. And then we have E plus A yields D. That's 350. Those are the equations we have to work with, and we need to use Hess's law to find out what's the enthalpy of this reaction. This is our target reaction. B yields E plus 2C. Okay? So how do you approach a Hess's law problem? You look at the target equation and then work your way backwards by identifying which ones of these will give you the terms that you need. Okay, so if we need B on this side, where do we have B? We've got B here and we've got B there. So maybe we had better off to look at a different one. Let's look at E. Let's do E first. So E needs to be on that side, but here it's on the left. So that needs to be flipped. So it needs to be D equals A plus E. Okay, that means this value is minus 350. Okay, so we got E covered with this one. Okay, how about C? Well, there's 2C. Right? It's on the correct side. So we got this one. It's got C where it needs to be. Okay. Now we got this one left over. Notice that we've already got B taken care of, but there's too much of it. But we've also here introduced A. But A is a whole 1A on that side. We need to make A on this side equal to whole, right? If we have a whole coefficient of 1 here and coefficient of 1 there, then A's will cancel. And notice we had no A's up there. So we need to get rid of that A. So this one we're going to multiply by 2. And that gives us A yields 2B, and then 2 times this is 300. So if we use that one, will that do what we want? Well, get rid of an A, and now it gives us 2 B's. 2 B's cancel 2 B's on this side, leaves us 1 B. Okay, so if we use this one, and this one, it might be easier to follow it if we just bring these 3 down, add them all together down here. Right? So on the left-hand side, we have 3B, and then A, and then D. And we go on the right-hand side, 2C, plus D. And then here, this one is 2B. And this one is A and E. Now, I'm not going to add the enthalpies yet because I got to be sure that this equation matches that one. Okay, so we got an A on this side, A on this side. Okay, we got D on this side and D on this side. They cancel. Then we've got two B's on this side, and that makes one B on this side. So there's our B, there's our E, and there's our 2C. So we do have the correct combination. Now we need to add this one, this one, this one. So what's this one? A negative 475. These two negatives, and then a 300. 175, a negative 175. So 55, is that correct? Negative 175 is C. Yeah. That's the answer. Okay? That's the way you use Hess's law. And I think it's easier to understand when we have these A, B, C's, and D's, what is actually happening here, rather than using elements and compounds. Now, eventually you're going to have to do elements and compounds. So let me see if I can find one that we can do before all my time's up. How about 65? Let's do 65. Fairly simple. There's just one trick. And I can kill two birds with one stone here. $65. Okay. We've got those two equations. I'm going to write them up here. Plus 1/2 of 2. Let's see. This is a solid. This is a gas. And this is a solid. Okay. And that's delta H under standard conditions is minus 144 kilojoules. Okay. And the second equation we have is this one, solid, yields copper plus copper 2 oxide. And its enthalpy is plus 11. Okay, the question is, use these two equations in combination to determine the standard enthalpy of formation for CuO. Right? So the first thing you have to do is you can't use Hess's law until you know what the target equation is. And they just told you what you need to do, standard enthalpy of formation. So remember how to write the equation for a formation of a compound. Okay? It's let's see. You write 1 mole of the compound first, and then you work backwards. Okay, and you form it from elements in their standard states. So copper solid plus O2, diatomic gas. Okay, those are in their standard states. Then you use coefficients here to give you 1 mole of that. After you write this and the arrow, you can't touch that. Not for standard heats of formation. Okay, so we've got 1 copper. That one's already good. We need only 1 oxygen. So this needs a 1/2 coefficient to give us 1 oxygen. Now, we want to use those two equations to give us this one. Okay? So, let's see what we got here. Let's see. Copper oxide is on this side. Let's see. That's the only place, it occurs in two places. All right, so let's look at the other ones. 1/2 O2, that's good. 1/2 O2. But we need copper on this side. Right. So let's leave this one where it is. And let's put the copper on that side. Plus CuO yields Cu2O. And this now becomes negative 11 kilojoules. Okay. So we got copper on the right side. We got the oxygen on the left side, copper on the left side, oxygen on the left side, and CuO on the right side here. Will that give us, if we use this one and this one, will that give us our target equation? So let's bring them down. And we're going to use this value and this value if this works. So we have Cu2O plus 1/2 O2 plus Cu plus CuO. That's all on the left-hand side of the arrow, this one and that one. On the right-hand side, we have 2 CuO and then Cu2O. Okay? Now let's see if we can cancel anything. Cu2O. Yep, there's one of them on both sides. Here. Okay? How about this one? CuO. Well, let's see. What did I do wrong? Got this one here and here. This one here and here. We've got this one over here. But we've got one on this side and two on that side. So this one's gone, and this one is 1. Okay, we're good. Now we can add these two together. So minus 11 and minus 144 is minus 155. So that's E. E is the answer to this one. Okay. Let's see. How we doing? I think I'll run out of time. 2 minutes. Let me see. I had 70 picked out. So, which ones did I skip? 55. Oh, 59. I skipped 59. So you want to check that one out. That one takes a little bit more work. It'd be more than 2 minutes worth. And what else did I skip? 35. We did 35. Okay, that's good. 29. I think I skipped 29, didn't I? Yeah, I believe I skipped 29. I think that's all. Oh, 25. 29 and 25, I did skip those. I believe I got everything that I wanted up to that point. So take a look at those. And they will be covered in the Greenbrier video that I'm going to put a link for you. You can check those out.